Hi students, welcome back once again to askIITians. Now to continue with the chapter that I was discussing in the last class about the kinetic theory of gases, it's a time that we should now move over to the energy distribution. So for example, in the ideal gas, the energy is distributed either in the forms of translational kinetic energy or the total of internal energy. So in this today's session, I'll try to explain you everything in detail about the translational kinetic energy as well as something about the internal energy of the molecules of the gas. Now, let us start away with the session, and after this session, we'll also discuss something about the law of equipartition of energy. So now let us begin up with the session properly so as to go step by step to all the topics that I have taught you. So students, now let us come over to the new topic where I'm going to tell you something about the molecular kinetic energy and internal energy. So whatever we have learned so far related to the ideal gas equation and the kinetic theory of gases, now we'll move ahead out of those two topics and we'll try to study what do we mean by the energy. So then we're going to define something about the molecular kinetic energy and what is the overall internal energy. So let me first of all discuss what are the learning objectives. So when we'll do the molecular kinetic energy and the internal energy, so once I'll be telling you all these things, all these topics, so by the end of this chapter, by the end of this topic, you will be able to explain as well as you'll also be able to use the translational kinetic energy of the gases. So there is a formula which is written over here that the kinetic energy, translational energy, is nothing but 3 over 2 R over Na into T, which is nothing but 3 by 2 kBT. So where come we got this formula from, and what are all the places where you can use this formula? So at the end of the chapter you will be able to discuss everything about this thing. Moreover, we'll also be able to discuss something about the principle of equipartition of energy, and also we'll discuss something about the degrees of freedom. Not only this, I will also let you know, like we'll discuss we'll also state the number of degree of freedom for monoatomic, diatomic and polyatomic molecules. So we'll take into account one by one all the different type of gases. We'll try to find out what are the degrees of freedom associated with these particular gases, and finally you will be able to calculate what is the total kinetic and internal energy. Now let me explain these things in a little more detail. So the molecular kinetic energy and internal energy will be discussed in this particular section, and you will also be able to explain the internal energy of gas, and you will also be able to correlate that internal energy with the number of degrees of freedom. So this is what I told you. We'll take into account different gases. We'll try to find out what are the degrees of freedom for those gases, and then we'll try to correlate them to the internal kinetic energy. So these are the formulas that we'll be deriving by the end of the chapter, and you'll also be able to explain and use the internal energy of any particular ideal gas. So let's start away with the topic where we are going to discuss something about the molecular kinetic energy and internal energy. Let me first of all define what do we mean by the translational kinetic energy of the molecule. As per whatever we saw in the previous slide, I told you that there is a gaseous molecule which is moving with some speed which is known as the translational speed towards one of the walls of the container. That means what? The molecule possesses some translational kinetic energy, and just in the previous slides we have seen that P was represented as 1 by 3 capital N into M by V into V square. So this was the pressure how we represented. Now if I ask you to simply divide and multiply the above equation by 2, so you will say P will be nothing but 2 by 3 into N by V into 1 by 2 Mn V RMS then square. Now the question rises, why am I doing so? I basically want to get some term like half mv square which I can correlate to the kinetic energy of the molecule. That means if I just look into this equation, I can analyze this thing. When the pressure increases, so if the pressure will increase, let us try to find out what are the conditions when there can be an increase in pressure. So I will say the pressure will increase when either N by V increases, so this is the first factor. So with an increase in N by V, you can say that the pressure increases, Also, you can say that if you increase the second factor, this kinetic energy factor, if you are going to increase, then also there will be increase in the pressure of the gaseous system. Now let us study in little more details about the translational kinetic energy of the molecule. So this is what we have done earlier also, that with the increase in N by V factor, either the pressure can increase. Also, if you increase half mv square factor, then also there can be an increase in pressure. So if I rearrange the equation which I have written in the above part, then I can say that pressure into volume is nothing but 2 by 3 into N into half m V square, then there is an average sign. So I'll just ask you to go back to the previous slide where we can see, if I take this volume to the left hand side, so I get a term of PV is nothing but you have, so here we see PV is nothing but 2 by 3 is a separate term and you have taken outside, and hence you are keeping something as a kind of kinetic energy of the molecule. And we also know this thing that PV is equal to N kBT, where kB is nothing but the Boltzmann constant. So if I ask you to correlate these two things as we have done in the earlier class also, I can simply say that N kBT is equal to 2 by 3 into N into half m average of V square. So if I move ahead, let me try to figure out what do we mean by this thing. N got cancelled. So here you can cancel the value of N. You can see that this half mv are V simple square. So that means half mv square is nothing. You take 3 by 2 over there. So you get it equal to 3 by 2 kBT. And you can also correlate this thing to the fact that you have written here half mv square is nothing but K translation. So it's just about correlating the two things. So the translational kinetic energy of the gaseous molecule is given by this particular formula. Now if I tell you the little more details related to this particular formula, you can find that K translational is 3 by 2 kBT, and we know kB is nothing but Boltzmann constant, which is R over Na. So it is 3 by 2 into R over Na into T, where K translational is the average translational kinetic energy of the molecule. So now you have been given what do we mean by the average translational kinetic energy of the molecule. So if I move ahead, I can say that T is the absolute temperature. So in this formula, T is the absolute temperature, Kb is the Boltzmann constant, and R is the molar gas constant or the universal gas constant, which we have discussed in the previous slides. And Na, as per we know that Na is the Avogadro's constant. So let's study little more details about this particular formula. I can say that for n molecules of the ideal gas in a cubical container, so earlier we had taken that there was a cubical container in which there were n molecules of the ideal gas, the total average mean translational kinetic energy. See, we just found out what was the average kinetic energy for just one particular molecule, and I had written it something as 3 by 2 kBT. If I am saying that there are total number of n molecules, and if you want to calculate what is the total average translational kinetic energy, you multiply it by the factor of n. That means now you will get the total average translational kinetic energy E. So you can say the total E is nothing but n into K translational for only one molecule. Moreover, you can also correlate this thing to E will be nothing but 3 by 2 into nRT, where n is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin. So once we are done with this particular thing, let us try to move over to what do we mean by the principle of equipartition of energy. Let's say the principle of equipartition of energy states that the mean or average kinetic energy of every degree of freedom of a molecule is therefore defined as half kBT. That means for this thing we should know what do we mean by degree of freedom. So degree of freedom, to tell you in short, it is basically stated the number of coordinates which are required, the number of independent coordinates which are required to completely define the position of any gaseous atom in the state. Now, According to the principle of equipartition of energy, it says that if I am asking you to calculate what is the average kinetic energy of every degree of freedom, it is nothing but a value as half kBT. So, if you know what is the total number of degrees of freedom, you know what is the total kinetic energy associated with 1 degree of freedom. That means you will be able to find out what is the total kinetic energy associated with all the degrees of freedom. See, here in this formula I have said for 1 degree of freedom the kinetic energy is half kBT. And if there are f degrees of freedom, then the total kinetic energy, which will generally be an average value, it will be some f by 2 into kBT. So I have written it as average kinetic energy. Or I can also call it as mean or average kinetic energy per molecule. See, so here also if I say this is mean or average kinetic energy per mole, then if you are talking about per molecule, you need to take into account the Boltzmann constant. However, if you are talking in the terms of per mole, you need to take into account the universal gas constant. So F is known as the degree of freedom and T here is known as the absolute temperature. Now since we are done with this particular topic, let us do an example so as to understand whatever we have done and so as to quantify this thing. Now the example says that a vessel contains hydrogen gas of 7.50 into 10 raised to the power 17 molecules per unit volume. That means in a unit volume you have been given what are the total number of molecules of hydrogen gas which are present. And the root mean square speed of the molecule is 2.5 kilometers per second. So he has also given you what is the RMS speed of the molecule. And the temperature is given to be 30 degrees Celsius. So you have been asked to determine the average translational kinetic energy of a single molecule of hydrogen gas, first part. And the second part is the pressure of hydrogen gas you have to find out. So given that the molar mass of hydrogen is 2 grams per mole, Na is given to be as the Avogadro's number and K is also given to you as the Boltzmann constant. So now let me tell you how do we proceed for any such question. We very easily know that the number of molecules per unit volume for hydrogen gas in this case is given to be 7.50 into 10 raised to the power 17. Moreover, the VRMS is also given to be some 2.50 into 10 raised to the power 3 meters per second. So see, I have converted the kilometers range into the meters. Now the temperature is given to be 303 Kelvin. So since all these things are given to us, let me first of all begin with the first part. We have to find what is the average kinetic or translational kinetic energy. So to find what is the average translational kinetic energy, K translational, and we need to find it for just one particular molecule. This is 3 by 2 kBT. Now we know 3 by 2, we know kBT as 1.38 into 10 raised to the power minus 23 into 303.15 Kelvin, and hence the value will come out to be 6.28 into 10 raised to the power minus 21 joules. So this is how you have to proceed with the first part. Let's go over to the second part now. In the second part, we know that we can use this formula. P is 1 by 3 into N by V into M into V square. Then you have to take an average of the two things. Now we also know that. So we can also say that M is equal to capital M by Na. Whatever is the molar mass, you have to divide it by Avogadro's number. And you should know that this is equal to V RMS square. And why so I have written this thing? We know that V square under root is nothing but V RMS. So if I take the square on both the sides, V RMS square is nothing but you take the average of the square of the velocities. So if you simply put the values, you will get P is nothing but 1 by 3 into N over V M divided by Na into V RMS square. Now all the values have been given to us in the question. P can be written as 1 by 3. This is some 7.5 into 10 raised to the power 17 molecules were present per unit volume. So N by V is value as 7.5 into 10 raised to the power 17. Then the mass is 0.002, which is to be divided by 6.022 into 10 raised to the power 23, and the velocity is 2.5 into 10 raised to the power 3 whole square. So if I ask you to solve this value, you will get the pressure nearly 5.19 into 10 raised to the power minus 3 pascals. So students, see, this is how we have to simply first of all do the derivation, keep the concept in mind, and then try out doing the questions for such topics. So students, in this lecture, as per you have seen, we have discussed something related to how the energy is distributed among all the different molecules of the gas. We discussed about the translational kinetic energy. Also, we had a discussion about the total internal energy. After the discussion of these two particular topics, we had also discussed something about what do we mean by the law of equipartition of energy. Having done this thing, now it's the time that we should move over to another topic. So in the next session, I'll introduce you people to something known as degrees of freedom. So by that time, what I'll ask you people is to revise whatever has been taught to you till now. Stay tuned and be happy. So meet you again in the next session.